pleasure to introduce Professor Pilanci from Stanford University. And Professor Pilanci graduated in 2016 and from Berkeley. And he has been working on very fundamental optimization method for non-convex and object function. I think that will be very interesting to many of us because some of us are working on the neural network, which is the linear non-convex optimization problem. So, okay, so without further introduction, so give the floor to Professor Pilanci. Let's welcome.
Thank you. Thank you for the introduction and thank you for inviting me. It's my pleasure to be here. So today I would like to talk about my recent work on randomized algorithms for large-scale optimization. I'll start with some challenges. So one problem we have is, as all of you know, the scale of data. So we have this exponential increase in the amount of data we have. Every day we create something like 2.5 billion gigabytes of it. And in fact, stored data grows faster than world economy. So this makes us think we should come up with some different ways of storing, analyzing, optimizing using large data sets. We have data sources from networks, Internet of Things, connected devices with lots of sensors. We have very large collections of text from news sources, online websites. We have very large image collections. And we have already seen the impact of big data. So we have witnessed the deep learning revolution. So these are very complex machine learning models. Each of them is actually more and more complex. These are actually based on non-convex optimization. So for tasks like image classification, scene understanding, telling us which objects are in an image, they do extremely well. In fact, in many benchmarks, they can beat human accuracy. So you see the reverse trend. So the accuracy is increasing, the error is decreasing. So in many problems, machine learning, statistical estimation, maximum likelihood estimation, exploratory data analysis, optimization is key. Often the problem boils down to finding the minimum of a function subject to certain constraints. And the optimization actually is very common in control theory, adaptive filters, Kalman filters, imaging problems, inverse recovery, designing, manufacturing, and decision making. Optimization is very, very common. So that's the problem with big data. So as you get more data points, you usually increase accuracy. But now we have to solve very large-scale problems. And if you use more complex models, like very complex deep nets, these problems become non-convex. They are even harder to optimize. So convex functions are the ones which curve up. And when I find a point which has zero gradient, it's stationary. It's a local and therefore a global minimum. But for non-convex functions, it could be a local minimum or it can be a stationary point. So it's even harder if you have a non-convex problem and very large data sets. So the problem I would like to pose is, what if we could reduce the data volume without losing too much? Okay? Now I will tell you what this means, what's significant information we would like to preserve is very soon. But this will help us solve very large-scale optimization problems, convex and non-convex. So there will be three goals in this talk. First one will be finding optimal trade-offs between computation and accuracy in an optimization problem. So ideally, as the data size increases, the computational cost, we want this to be linear. And linear is ideal because at least you have to read the data. Okay? So you can't do much better than linear. But optimization problems often require higher than the linear complexity, like quadratic complexity for least squares type problems, even higher n to the 6 complexity for semi-definite problems. So this is the curve we would like to achieve. And then to try to leverage distributed computation, we are already at the limits of centralized computing, so we would like to utilize lots of parallel GPUs, lots of nodes in a cluster. And then third one will be tackling non-convexity. How can we deal with non-convex optimization? These are very hard problems, but we can have heuristics. And the thing is, if we make the heuristics faster using techniques like compression, can we say something concrete about these results? Can we prove maybe global optimality? So these will be three goals in the talk. So I will talk about sketching, describe what it is, and then how they work in a distributed environment when you have multiple machines, multiple threads, and then introduce some non-convex problems and talk about sketching in non-convex problems, then describe some ongoing work. So let's start with something very simple. Let's say we have a convex optimization problem. So f is a convex function. A is a data matrix. A is n by d. I have n samples and d dimensions. And A is very large. N and d are both very large. So for now, you can assume n is larger than d, but it's not going to be important. D could be much larger than n, and the same story will still apply. So I would like to minimize f of ax subject to x in a convex set. So for instance, support vector machines, logistic regression, these are all of this form. Or if you would like to train a deep net and then later add a final layer, it's going to be a convex optimization problem. So few examples of large data sets. The airline data set, it's 120 million flights. Their flight details for over 21 years. And D is very small. Okay, so it's an extremely tall data matrix. Another example is the ImageNet dataset. It's 1.3 terabytes, 14 million images, and D is the image pixels vectorized, so it's a couple thousands, still extremely tall and thin, but very large. But it could be the other way around. It could be the case when N and D are replaced. D is much larger than N. It's also possible. It will end up looking like the same problem. So in these scenarios, we are often in this shape. We have the data here. Okay, assume these are my rows of this large data matrix. These are my rows. These are the columns. And then we have an optimizer here. So you are running an algorithm to optimize some function. So let's say we take the first batch because this is the amount that will fit into my machine, okay, or GPU, or main RAM. This is very often. So you just look at a small batch. And let's say there is a cost function using all the data. Using the entire data, there is this cost function. And there is a parameter that minimizes this cost. I would like to find this parameter here. Okay, it's my maybe machine learning models. It's my optimal parameter. So based on this small batch, you will only see a sample cost function based on this small data, right? And if you haven't seen the rest, you have no idea how the others one will look like. So if you take this one instead, maybe it will be this. If you take another one, it will just jump around. And in general, there could be no guarantee how the next data batch will give a cost function to you, right? It will be totally uncertain. So the idea behind this talk is, what if we compress the data set before and then have here a compressed small data batch, right? So the hope is that the combined compression will give you a cost function like this, which might be very, very close to the original. That's the entire idea. Can we compress and maybe combine these data rows together into something very small? Well, this might work because at least if you do this, now every row here gets to touch my optimizer. Somehow I am affected by these rows. Unlike when you sample, you don't ever see what's going on with the other data rows. And these are going to be basically some weights. I will linearly combine them. But it will turn out that these weights are not important. I will just set them randomly and it will work. Okay? And then later you might figure out what the optimal weights are. But there will be something very simple, which will allow us to just linearly combine this data set into a representative small subset. And let's take something even more simpler, the least squares problem, which is convex. So in this case, A is n by d. It's my feature matrix. Y is my n-dimensional response. I minimize the norm of ax minus y, norm squared, subject to some constraint. So this is my f of ax function, which is f is convex. And this optimal value I denote by OPT. It's some value. It's a real number. So here's my matrix, n by d. N is large. So the idea of linearly combining and compressing can be written linear algebraically as a matrix multiply. So I have an S matrix. It's m by n. When I multiply, you get S times A, which is very small, m by d. Okay? In this context, S is called a sketching matrix. So, for instance, every entry here, I can pick IID plus 1, minus 1 from random coin flips. Okay? This is also called a random projection matrix. It's all the same. It's a random matrix reducing dimension. And then the idea is this small data set, I can do anything with it. This can fit into my GPU. I will solve the smaller problem using S times A, S times Y. This will be my approximation. And I will use this as an approximation to the original minimizer. So what's the intuition behind this? So this is actually a theme which recurs in signal processing and information theory. So you would like this norm to be equal to the other norm by a choice of the matrix S. If S were an orthonormal matrix, if S transpose S was equal to identity, they will be exactly equal to the same, right? Because those matrices preserve norms, they just rotate. But it's impossible in this case because the columns of S can't be all orthogonal to each other because you have n columns in m dimension. They can't be all orthogonal. But the next best thing you can imagine is approximate orthogonality, right? And if you just generate plus 1, minus 1 numbers here, they will be uncorrelated. They will be almost orthogonal. So that's the intuition behind why such a scheme might work in approximating the original function, okay? And there are other ways to generate this matrix S. For instance, you can pick a discrete Fourier transform matrix and only use a diagonal plus 1, minus 1 matrix here. So F times D. And then you will pick random frequencies out of this discrete Fourier transform matrix. So this is inspired by compressed sensing, work of Candice and Tao, and also Donahoe. This will also give you a dimension reduction, which is as good as the plus 1, minus 1 flips. But this is way more efficient because I just need to compute one discrete Fourier transform, and it can be done in n log n time. Okay, so this whole operation can be done very fast. So this is as fast as reading the data. It's near order ND, near linear, omitting the logarithmic terms. So as fast as I can read the data, I can form this as a multiply in order ND time. So here's a theorem. So theorems like this existed before, but we improved these results and then tightened the bounds, and we also proved the converse. So it says if you choose this m, small dimension here, 2 times the rank of A divided by epsilon. Epsilon is a parameter like 0.1. Then the x hat you get from here, if you plug in the original function, it's always worse than the optimal, obviously, because this minimizes it. It's never worse than 1 plus epsilon times the optimal value. So it's an epsilon approximation in terms of the objective function. And this rank here is actually what we call effective rank. So which is the number of, so the rank of the effective part of your data matrix. If you have a constraint, such as an L1 norm constraint, you will see lots of the entries are 0. And there will be an effective part of the matrix, which is just the indices corresponding to the non-zero ones. And it's an extremely small matrix. It's the rank of that effective matrix. If you have an alter regularizer, it's going to be like a weighted soft measure of rank. It's usually much smaller than rank. But I will tell you what this is very soon. And here's a converse. If you choose m less than this, which is about a constant times rank, this constant is less than 2, like 1 over 16 or something, divided by epsilon, then it is worse than 1 plus epsilon with at least a probability half. So it doesn't work if you decrease m to a constant multiple of rank. Okay, so here is a practical application. If you have the airline data set, n is in the order of millions, d is very small. I don't really know the rank of this matrix, but it can be at most d, right? The rank could be at most d. So according to the theorem, rank is at most 28. And if you set m equal to 500, you will get a 1.1 approximation. And if you set m to 5,000, add one more zero here, you will get one more zero here. And the theorem, the converse, says this scaling is tight. If you add one zero here, you will get another zero, and you can't do any better than this. Okay? And the converse is proved using information theory, using the capacity of multiple wireless channels and communication limits, because essentially the sketching matrix is like a channel. It likes to transmit the data to you, but it's limited in its capacity because it's reducing dimension. Okay? So here's actually what happened. There was an original cost, this one, and there was an approximate cost which corresponds to this one. And the theorem says if you minimize this and then transfer this value here, look at the objective here, there will be at most an epsilon gap vertically, right, in the vertical space. But you might argue the vertical distance is not so relevant in many applications. In objective value, you can get very close, but how about the solutions? The solutions are sometimes more important. It's the signal you would like to recover, for instance, in signal processing. Now the question is, the next question is, how big is this horizontal distance between the solutions? And when we ask this question, so very interesting things will pop up. So I'll talk about the statistical version of this problem. If we have a statistical model, statistically how close are the vertical distances, how close are the solutions? So let's take least squares. So Gauss invented least squares in 18th century. And in signal processing, we are still using least squares because it's the optimal solution to linear equations when you have Gaussian noise. So you have response. Let's say the noise is Gaussian on this response, and there's a linear model. This will be the optimal thing to do. In 2 dimensions, it's just fitting a line, fitting the best line, minimizing sum of squares of the vertical distances. And here's a model which makes sense with Gauss's model Gauss's observation model in mind. Y observation is equal to A times X star, and X star is some true vector, plus W. W is this Gaussian IID noise source with variance sigma squared. Then least squares would be the maximum likelihood solution for X star. And we can look at its estimation error. If I find the least square solution, compare it with the ground truth in this model, squared norm, expected value will be like d divided by n times the noise variance. And this is a very classical scaling in statistics. If I have n measurements, n equations, d unknowns, d parameters, the error decreases like d divided by n times the noise variance. Okay, very classical scaling in statistics. So a very natural question is, if I apply the sketching method for least squares, okay, I will approximate the X star using X hat, using the sketch data. Is this optimal, right? So if you do simulations, if you increase the number of samples, look at the mean squared error, which is the expectation of the squared prediction error, you will see that least squares will do very good, and it will have the correct scaling. In logarithmic terms, it will decrease linearly, but the sketch solution will not. it will have a very large error. And we were wondering why this can be true. Like, is this suboptimal, or is it optimal, or we can't see it yet? It turns out that it is suboptimal. And it's information theoretically impossible to get an optimal estimator after sketching. So here's a theorem. For IID plus 1 Gaussian or Fourier transform-based sketches, if you choose the dimension m, the dimension you sketch to, constant times rank, then the prediction error is always lower bounded by the variance, which is a constant. So remember, the other one decreases like d divided by n times sigma squared. This one will stay constant. So there will be like a lower bound. There will be an error floor that it would never go under. Okay, and that's a fundamental limitation of these type of methods. So there's a gap. We have a very fast way of estimating using the sketch. Computation is linear. Statistical error is suboptimal. If you do the original, for least squares, it will take like order nd squared time using QR decomposition or conjugate gradient algorithm, but it will be optimal. So there's this gap. Now, the natural question is there an optimal algorithm, statistically optimal, with complexity order nd, linear time in the data? So we have the entire data set. Suppose it's very large. Using a maybe supercomputer, it will take order nd squared time, but it will get statistical error d divided by n times sigma squared, which is optimal. But our computationally bounded machine, which operates on the sketch, runs in linear time. It doesn't achieve this using the regular sketch. Can we make it optimal? Maybe we can modify the sketch, right? Because the sketch was chosen at random. Maybe there's a better sketch that will get closer to the true solution. It turns out, yeah, there is. So let's say this machine gets S times A, and over the rows of S, it will look like the first row of the sketch times A, second row of the sketch times A. These are matrix vector multiplies from the left. Okay? And then next round, form the residual, which is A times the previous estimate minus Y, because the residual will tell you where the uncertainty is. And next time you don't multiply with something random, multiply with the residual, because it will tell you, it will look for the part of A which is uncertain, right? And then get this, instead of the sketch, multiply with the residual, and then get the second residual and iterate. Okay, so after the sketch, start multiplying with the residuals. And if you do this only log n times, logarithmic in n, you will achieve optimal statistical estimation. And this algorithm will still be linear time, order nd. And if you simulate this, we call this iterative sketch. It will match the optimal least squares solution, although this will have order nd complexity, this will have order nd squared complexity. And here's a theorem. Under this model, where x star can belong to any convex set, iterative sketching will achieve optimal prediction error with logarithmic number of iterations. And then it will be optimal both statistically and computationally. And this is true for any set. You can think about L1 norm, L2 norm, L infinity norm. It will be fast and optimal. So here's a practical application. So there was this Netflix prize a couple years ago. So the goal is to recommend movies. And the basic task you can think here is, given a movie, predict the scores. So you have a matrix of ratings, users times movies. We have 500,000, half a million users, 17,000 movies. It's very sparse. So very few movies are rated by users. It's a number between 1 and 10, the movie rating. And the simplest task would be pick a particular movie, predict the ratings, which a user haven't seen, right? And you can do least squares regression, basically, because it's a continuous regression problem. And you can do least squares with an L2 regularization. And a very typical thing to do is you partition into test and training this large matrix, and then solve for many values of lambda and find the one which minimizes your validation error, right? So you typically need regularization for these problems. So if you solve these ridge regression least squares problems with L2 regularization, also called ridge regression, with the MATLAB / operator, which does Cholesky decomposition, you will get this blue curve in the test error as you vary regularization parameters. And then you will probably pick this one, which will minimize your test error. So, but this takes 1,700 seconds, okay? This is like half an hour. So if you want something faster, you can do conjugate gradient, which is an approximate solver. It's an inexact least square solver. It will give you this black dashed curve, conjugate gradient, okay? And you can notice that it's worse. It's slightly worse because it's approximate, right? But it's very fast. It takes half the time. It takes like 10, 15 minutes. But you can see there's a gap in optimization. If you optimize more, you will derive the test error lower. So we are optimization bounded here, optimization constrained. So if you do this iterative sketch algorithm, not only you will match the test error of the MATLAB exact solver, but it will only take a fraction of the cost. So the iterative sketch will only take 100 seconds total. Because I just multiply with something random, make it very small, and then multiply it with the residuals very few times, in theory log n. It will be linear time, but it will match the optimal prediction error. Any questions on this application?
Yeah, actually on slide 16, you seem to have a slight deviation as you go above 10 to the 4. Is that real or is it just an artifact?
Oh, okay, you're right. This is probably because of a numerical error. When the error is very low, you get precision issues. Yeah, I guess so. Because we have random matrices. Yeah, I guess it's a precision issue. Okay, so in practice, the typical thing to do here is matrix completion and matrix factorization. But actually, if you look at the alternating minimization algorithm for matrix factorization, it is just least squares. It's just successive least squares. So you could have also done matrix completion with this algorithm too. So this was for least squares so far, least squares with constraints. Can we generalize this to arbitrary functions? Because we have lots of other functions like SVM, logistic regression, linear programs, neural nets. So how does this idea apply? So let's say I minimize f of ax, f is convex, and this is x star. I will tell you a story between first order and second order methods. So if we have the gradient descent. Let's say this is the cost function I would like to minimize. This is a two-dimensional function. These are the contours. This is the global and local single minimum. And let's say I start from here and I do gradient descent. So gradient points in this direction. And I take a step in this direction. Maybe I land here. Every iteration of gradient descent is order nd. If you have an n by d matrix, you just do a single pass, compute the gradients. And let's say you come here. It will take, let's say, 1 unit of time. Let's say 1 hour, order nd. And then in the second iteration, you will go in this direction and then do this, right? Gradient descent is very myopic. It only sees the direction of the most descent. The higher the largest descent. It doesn't see the curvature. It only sees the descent direction. And let's say you zigzag and come here. By the way, if you're only using gradient descent, you will obviously zigzag a lot. And if your function is more curved, you will zigzag more. But there's also this second order method, Newton's method. Starting from here, it calculates the curvature matrix, the matrix of second derivatives. Because it knows the curvature, it just takes a very clever step. And then let's say it comes to here. But it needs to compute the matrix of second derivatives, which is a d by d matrix. Every single entry takes order n time, so total it takes order n d squared time to even calculate this curvature matrix. And then it solves a quadratic problem, takes order n d squared time, and finds this very, very clever step. It takes, let's say, 6 hours. It's very close, but it needs another iteration. So in the second iteration, it almost finds it exactly, but the thing is, it's way slower than gradient descent. Gradient descent already gave you this point, which is maybe okay if you look at your validation error. Okay, so this is one reason why second order methods are not so popular in machine learning. They need the curvature matrix, d by d, order n d squared time, and then solve the step. But they are very powerful. So theoretically, they have this affine invariance property. So what does this mean? So if I take this function and multiply x with an affine transformation, transform x to t times x plus b, Newton's method is invariant. It will take the same steps. So if, for instance, if I stretch this function this way, right, it will be like a perfect circle. The contours will be the perfect circles. Gradient descent will do much better. Maybe it will just take 2 iterations. Newton's method will take the same steps because essentially the Hessian matrix deconvolves that affine transformation. It wouldn't matter. Or if you squeeze this function this way, it will be more curved. Gradient descent will have to zigzag more. Newton's method will not change. It will take the same number of iterations. Okay, so this is a big advantage in theory. And in practice, if you can do 1 iteration, but even doing 1 iteration is very, very cumbersome in Newton's method. So the question is there a linear time method which will take order nd? It will take more clever steps, but it will not be as exact as Newton's method. And maybe after a few steps, it will find it. And hopefully, it will be affinely invariant. It will not be affected by the curvature. So here's an idea. So we can write Newton's method as follows. It's a minimization of the second order Taylor's expansion where I have the gradient of my function and I have my second derivative matrix here. Let's say we apply the sketching matrix on the matrix of the second derivatives. Okay? So it actually applies on the factorization of the matrix of second derivatives. It is the square root of the Hessian. Okay? And I will tell you how it works. It's always doable in problems of the form f of ax. You can form the sketch of the Hessian without even writing the sketch. Because of the problem structure, everything applies on the data matrix A. So you minimize this, which is an approximation to the Newton's method step. We call this algorithm Newton sketch.
But you only do it to the second order term.
Yes, only on the second order term. The first term is exact, but you could have done the sketch also here. Or you can do sampling here, you can do stochastic, you can combine, mix and match. But this is the basic idea. Just do approximation on the curvature first. And it turns out that the iterative sketch that I was telling you about, the idea of multiplying with the residuals, turns out exactly Newton's sketch for the function least squares. So if you do this for least squares, you will automatically get adaptive sketching by multiplying with the residuals. Because the next gradient you get here will be the adaptive sketch. It just follows from a simple calculation. And here's a theorem. So Newton's sketch is affine invariant in distribution, which means you will get a random sequence of points. It will be a random process. The distribution of these points doesn't change if you do an affine transformation. It's like a stochastic version of Newton's method. And the number of iterations it has to make for epsilon accuracy is less than a constant times log 1 over epsilon. And this constant is universal. It's independent of your function and the data. So this is the important bit, because gradient descent, and actually any first order method, the number of iterations they have to make to find an epsilon approximate point in objective value, it has to scale with the condition number, the curvature number. So the computational cost of gradient descent, and actually any first order method, scales with kappa or square root of kappa, some depends on kappa, times nd, because nd is the cost of getting one gradient, times log 1 over epsilon. And actually Nesterov showed that this is the same for any first order methods. The dependence on kappa is unavoidable. Any algorithm that uses a combination of gradients and past gradients has to do a number of steps which scales with the condition number. But if you do Newton's method, seeing the curvature just breaks this barrier, you will get no kappa but nd squared. But if you do Newton's sketch, you will get order nd, no kappa dependence, no curvature dependence, times log 1 over epsilon. So here's a simulation. If you compare this method in logistic regression, 500,000 examples, these 5,000, you will see Newton's method in whole clock time is very slow, and gradient descent actually does the best early on. Newton's sketch is better only after certain accuracy. But if you switch to, this was for the uncorrelated features. This is a random feature matrix which is generated uncorrelated, so it's not curved. The objective value, the objective function is not, does not have high curvature. If you switch to correlation 0.1, now the columns are generated randomly. The correlation is fairly small. Gradient descent will have to zigzag, but the Newton sketch will not change because it's affinely invariant in distribution. Okay, so it will be independent of the curvature of the data. And we can apply this to some problems which have extremely high curvature, like solving linear programs. If you have this objective minimize C transpose X, A times X is index-wise less than B. These are very common in signal processing, industrial engineering, lots of other areas. So it's very common to employ a barrier method for these type of constraints. Instead of making AX less than B exactly, I will have a barrier function which will force me inside this set. Okay, so as I get closer to the barrier, this log will blow up to infinity, minus infinity, and then I will be forced to stay inside. This function I minimize with Newton's method usually because it's extremely highly curved, very high curvature. So if you do Newton steps, you will follow this black curve, and in the direction of C, this is the vertex optimizing C transpose X inside the constraint AX less than B, which is this polytope. If you do Newton sketch, you will take a random path. Every single time you will take a random path, but it is provably convergent to the optimal solution. Of course, every step takes way less computation than Newton's method because you don't even form the matrix of second derivatives. But the steps you make are invariant to affine transformations. It's invariant to the curvature. Okay, now I will talk about the distributed version of this. So how can we utilize lots of machines, lots of threads, maybe multiple GPUs? So let's say I have the first part of the data in my machine, and I have lots of other machines. Maybe they are physically separated. Maybe these are threads on the same machine. Each one of these machines or threads are working on a small batch. Okay, let's say we are in this setting. And to find the optimal, there has to be some communication because the optimal parameter depends on the entire data. There has to be some communication. Let's take the simple least squares example. Let's say I have the n by d feature matrix and I have y. I partition A into 2 over the rows A1 and A2 and y1 and y2 correspondingly. And the least squares cost over the samples decomposes as this. The cost over A1, y1 and A2, y2. The parameter x is the same. I would like to find the x which minimizes this sum. And ADMM algorithm, alternating directions method of multipliers, is actually very classical. It's very well fit for these type of problems where you have A1 and A2 on different machines or different threads. So the idea is very simple but extremely powerful. So you just make this 2x different, call this x1, call the other one x2, different variables, but enforce equality. It's the same problem, right? And then you just take this equality constraint and put a Lagrange multiplier. And you will enforce equality by this Lagrange multiplier. But now I have to update my lambda, update my Lagrange multiplier parameter so that x1 equals x2. So on the first machine, you do this update, and you also add this term for stability. It will make x1 and x2 close in Euclidean norm, but you need this parameter rho. And in the second update, in the second machine, you will do another update. The thing is, the first update depends only on a1 and y1 because this is constant, the value of x2. On the second machine, you just update x2 while x1 is constant. And then communicate the values, update lambda. This is like a control system. You are doing feedback control to drive the error to 0, which is x1 minus x2 L2 norm. Okay? But in practice, you have to find a value of rho which converges fast enough. And you have to do a couple trials. And the value of rho and the convergence speed also depends on the curvature. So informally, ADMM converges in the curvature constant times log 1 over epsilon iterations. The curvature number can be quite high, can be very high. And the number of iterations here is actually the rounds of communication. So it affects a lot when communication is expensive. Communication between GPUs are expensive. Between physically separated machines is even more expensive because they have to wait for each other. It has to be synchronous. So this is something I really want to minimize. So here is the intuition. It turns out that we can interpret ADMM as a sketching algorithm. If you define two sketching matrices, one has identity block here, 0 here, the other has 0 here, identity here. Basically, the first sketch times A gives you A1, the second sketch times A gives you A2. It's a form of sketching, maybe not randomization per se, but it's just sampling. It's a dimension reduction tool, these matrices. But these are not random, right? These are very particular choices of A. And we can say ADMM is operating on naive sketches. Naive because it's just 0 and 1. It's not mixing entirely, right? It's doing local sampling into 2. So what happens if we do sketching? So now we will take linear combinations, get S1A here, take another set of linear combinations, get S2A here, right? One instance, for instance, is the DFT matrix with randomly permuted rows. It will be a random orthogonal matrix. S transpose S is identity. I will have random frequencies over S1, random remaining frequencies on S2, right? And I can actually distribute over those S1A, S2A. Essentially, I'm distributing in the Fourier space. After the Fourier transform, I'm distributing it. It's basically the same problem because the DFT matrix is orthogonal. And instead of splitting the identity in time domain, I'm splitting the identity in the frequency domain into 2, right? So you will do the same updates. But it turns out that if you do this randomly by mixing everything together, you can always choose rho equal to 1. And this turns out to be universal for every data. So here's the theorem. This is joint work with Emmanuel Candes. If you do it randomly, for instance, using the random DFT frequencies. This version of ADMM, which we call Randomized Direction Method of Multipliers, RDMM, converges in constant iterations. This constant is independent of the data. And rho equals 1 is universal, which means I only need constant log 1 over epsilon rounds of communication. This is optimal because I need to exchange d times log 1 over epsilon, order d bits information theoretically anyway, because they are solving a d-dimensional problem. Otherwise, it would have been equal to communicating d bits without communicating d bits. It will be information theoretically inconsistent. So in a random example, this is random heavy-tailed regression data. If you do ADMM with rho equals 0.01, you will get this convergence, iteration versus objective. If you increase it a little bit, it gets better, little more, it gets better. Now, little more, it gets worse, right? If you do RDMM with rho equals to 1, it will look like this. And it's universal. You don't have to tune rho. Yeah, so this is good, but we only know how to do this for quadratic problems. And there's lots of other forms of ADMM which are interesting to analyze in this sense. Those are open. We don't know how to do randomized splitting in other problems, like when you have L1 penalties, when you have nuclear norm penalties. So I will describe you another extension for non-convex optimization problems. These are very hard. The objective function looks like this, and we need to make further assumptions. One simple example is nonlinear least squares, or fitting a nonlinear model to Y, nonlinear regression. So here AI is my data point. F sub x gives you the nonlinear fit, and x are the parameters. And there's a heuristic called Gauss-Newton method, which linearizes the function using Taylor's expansion, but it does it different than Newton's method. It expands the function inside the Euclidean norm, and it uses the first order approximation so that you only get the first derivatives here. You expand this nonlinear function at certain point, x sub t. You get the Jacobian matrix because it's a vector function, and then you just minimize this over x. Linearize and then minimize. Same idea, but you expand it inside the function so that every single time you get a least squares problem. This J is Jacobian, and it is actually hard to compute in practice. Typical examples are learning neural networks, single index models and statistics. This is, for instance, a cost function for two-layer ReLU. It has stationary points. It has local minimums. It can be fairly complicated. So we define a randomized version of the Gauss-Newton method, the same way we did for the randomized Newton method. So you will multiply the Jacobian and everything else with a random matrix and make the Jacobian smaller. But the key point here is the random S matrix times the Jacobian can be computed by backpropagation. So the matrix vector multiplies with the Jacobian can be computed the same way you would compute a gradient. There's a backpropagation for it. It's actually known since early 90s, 1994. So this makes it efficient. And here's a theorem. This is very restricted, but it's a first step. So if you have a single hidden layer and your input data is Gaussian, which is very unreasonable, I know. But if you do this randomized Gauss-Newton method, it will find the global minimum in constant iterations. And the Gaussian input distribution is the only way we can prove it, but it's certainly interesting to go into other types of distributions like sub-Gaussians.
So where does the Gaussianity come in for your theorem to hold?
So it's because the Jacobian matrix and the S multiplication, we can only analyze it through explicit moment calculations. You have to know, for instance, what is the expected value of J transpose J. These type of calculations are very hard for non-Gaussian data. But in practice, this algorithm will work. For any data, you can apply this. And here is actually an example. So the classical MNIST dataset, this is a collection of handwritten images. You feed it here. At the output, you would like the correct digit to light up at the final layer for digit classification. So here's a comparison of SGD, batch SGD, the Gauss-Newton method, the original one, time versus training error, time versus test error, and the randomized version of Gauss-Newton method, both the normal version and the one which uses the iterative sketch. So Gauss-Newton method is not very practical, as you can see here. It will derive the error very fast after some point, but it takes, the initial couple steps will take very, very long. So the randomized Gauss-Newton method looks like it does the best if you have very limited, if you have a time limit. But the iterative version of it, which iterates over the sketches using the residual, does even get a better test error because now the sketch is adapted, it's more accurate. But for many purposes, this is good enough. And I think this is one example you see why Gauss-Newton method is not so popular. SGD will always beat it initially because it's very fast early on. But if you have a fast way of approximating the Jacobian, I believe that in practice, even for deep nets, these type of methods could be practical. They can be fast if you can approximate the Jacobian. So I talked about sketching, lower bounds, upper bounds, statistical optimality, distributed sketching, and non-convex problems. So let me tell you about some ongoing work we have in our lab. So one nice application of sketching is actually streaming optimization, when you have the data coming in continuously. For instance, adaptive filtering or Kalman filtering. So this is a paper by Martin Vetterli from EPFL and his student. So they actually applied our algorithm iterative sketch to adaptive filtering. So the classical algorithm here is recursive least squares, which is the online version of least squares. As soon as an observation comes, you update it. But it needs a matrix inversion, right? So you apply the same idea I described, which is approximate the Hessian by a random projection. And then you get a sketched adaptive filter, right? And the other extreme is the LMS algorithm, which is just SGD. There is no Hessian. You just go in the negative gradient direction by just using the online observation. So you see RLS does the best in MSE. LMS does the worst. If you do iterative sketch, it matches the RLS. But it is way more efficient. You don't store this matrix of second derivatives. You just store a very small matrix. And you can tune how many sketches you would like to use. If you change the number of sketches you use, you get a continuous transition actually between RLS and LMS. So if you have a practical application, there is a knob you can adjust to make a trade-off in time versus tracking accuracy. And the sketch, when a new data point comes, can be updated very easily because if you have A, I'm going to have a new row just beneath A, and it will actually, it needs to be multiplied by the new column in S. But if S is IID, I just keep the old S times A multiplication, and I just form a new S times the new A, right? It can be updated online. So another place we are experimenting with is privacy-preserving optimization. So if you have things like these smart home devices, they need access to certain data to give you recommendations, to make predictions. So they have to solve optimization problems to train their machine learning models. So if you don't allow this machine to use the data itself, but the sketched data only, they will still be able to optimize, they will still be able to learn. But from S times A, there is no way you can go back to the original data, right? So it will allow some privacy so that they don't learn about the data, but they can optimize over the data. And we can analyze how much information is revealed if you only reveal the sketch times the data by looking at the mutual information. And it can be controlled by choosing a smaller sketch dimension. Another application where this can be useful is fault-tolerant computing. For instance, when you have more than 100 nodes working on a problem in a distributed setting, it is very likely that some of these nodes are going to fail, or there is going to be some communication delay, so that you will not receive the part of computation from the straggling nodes in time. They will be very late, or they will just fail for some reason. And you will lose part of your data if you distribute the data directly over the rows. But if you sketch it and then send to these workers, send these nodes, they are just IID, right? If one is lost, I can generate another one, and I can send it to another machine, and I can do this in an online fashion. So essentially, data becomes almost like fluid. You can just generate a new batch, right, IID, and then start computing on a brand new instance. Okay, so that's all. Thank you very much for your attention.
Any questions?
Two questions. So first one is you show many like advantage of the sketch metrics, right? So what's the trade-off to use that?
What's the trade-off? Like, there are some cases where you don't want to use the sketch. Is this what you're asking?
What's the drawback if you use
Yeah, there are some drawbacks. For instance, there are some cases where you don't want to use the sketch because of the costs. For instance, if you have a very sparse data set and you multiply it with a matrix of +1, -1, you make the sparse data into dense data, right? It might be better to work on the sparse data if you have suitable algorithms. But it's not always, because actually GPUs, if you compare sparse matrix multiplication versus dense matrix multiplication of GPUs, GPUs are faster in dense matrix multiplication, even for sparse matrices. So there are trade-offs. If you have GPUs, yeah, you might sketch fit into the GPU, then this is very advantageous. But if you are on a CPU setting, which is not extremely parallelized, maybe staying sparse is better. Yeah, that's a good question.
It seems like your sketching though could help in situations where your data itself is noisy. Say, for instance, you have things where perhaps your sketching, in some sense, could reduce. In other words, the noise in your sketch basis is very compressed.
Yes, that's
right?
true. Yes.
So I can, one can imagine that it could help you. In a sense, it would help you denoise, quote unquote, your data.
That's true. I agree. Yeah, I agree.
Have you looked at that?
No. But that's certainly a direction we can look into. Also, when you have outliers in your data, let's say one entry is extremely large.
That's right.
When you sketch it, it gets distributed. So it's actually not an outlier anymore.
That's what I was thinking of.
Yeah, exactly. If you have clutter, it will be non-clutter when you sketch it. That's true. And another very related point is it can also help you in generalization error. So algorithms working on the sketch data might have a better generalization than the ones working on the exact data for this very reason.
Exactly.
Any other questions? Okay, so
Let's thank our speaker.
yeah, let's thank our speaker.